Welcome to Lecture 19, where we're going to talk about how we get our imaging geometry and calibrate our cameras. So as a reminder, we are using this pinhole camera model, which has a tiny hole that light comes in and then it illuminates the image plane, which is located a lambda distance behind this point. We have a coordinate frame for the world frame and then also a coordinate frame for a camera frame where Z is pointing outwards from that hole that the light comes through. We call that line along that ZC the optical axis of our camera. And so everything that we see in the real world comes down as little photons of lights, comes through that pinhole and illuminates the image plane. These are 3D points in the workspace. So we've got an X, Y, Z out here, and that gets projected a distance lambda behind our pinhole, and then it gets projected onto this plane, and then it has a location UV for its column and row placement. Now, for simplicity, we imagine that this image plane is actually in front of that optical center, and then we need to know what is the translation from our world frame into our camera frame. We need to know our projection from our camera coordinates into our image plane, and then we need to know our extrinsic parameters. What is this translation and what is the rotation matrix? Another step that we need to do is we need to go from the UV locations in our infinite precision world into our discretized, pixelized world over here. Typically, we have an offset because we start counting at 0 in some corner of our image. We need to take account that offset from where that optical center hits our image at OR, OC, and then we've got to round it to the nearest pixel value. Let me tell you a story. Last week, we took our robots to NASA's Neutral Buoyancy Lab. We have a bunch of images from the camera, but what we don't know is where are these cameras located, and what is their focal length, and what is the orientation of the camera. Somehow we've got to figure that out from the image. We are going to learn a technique that builds a system of linear equations and then solves those to figure out what our camera parameters are. And so how it works, you measure the location of a bunch of coordinates in the real world. So we get their XYZ location. You've got to throw a coordinate frame somewhere on there. And then you go to your image and you click on those points and record their row column values. From that data, then you solve and figure out what are your unknown camera intrinsic and intrinsic parameters. So today we're going to solve that camera calibration problem, but let's first do a review. So remember, we've got our real world coordinates, which are X, Y, and Z. And then there is this constant projection K that moves everything so that it is on a distance lambda behind that optical center. And then it projects it down onto U and V. These are actually in the camera frame. We can put a C on there for that. But we take this XC and we multiply it by K, and that gives us our U. We take our K times our YC and we get our V, and we have our K times Z, and that gives us a lambda. So we've got three different equations there. Our pixel coordinates are the U and the V, and then we can solve for what those U or V are because we can take this term right over here and solve for what K is. K is equal to lambda divided by Z, which means that U is equal to lambda times XC over ZC. And then V, very similar, is lambda times YC divided by ZC. Now, when we talk about our camera, remember that optical center gets projected down into a spot that we're going to call OR, OC. And to figure out where that is, we find it by using the vanishing point. And it's a cool idea, right? You put a cube into your workspace. There's my cube. And then you look at the vanishing point of parallel lines. So these lines have a vanishing point down here maybe, and these lines here come over to the vanishing point here and here. That forms a triangle. And if we take that triangle then and we look at where its perpendicular bisector is, so remember the perpendicular bisector comes from here, perpendicular there, and then this one comes over here, perpendicular here. This one comes here and it's perpendicular here. That point over there is the point OR, OC. So now our pixel coordinates are not UV, they are some row column values. And so we now need to convert these to that. And so we take our U and we divide it by some length, SX, our scaling factor in the X location. And that gives us what is our R minus our principal point. And similarly, to figure out what our V value turns into, it's equal to our column minus our OC. And typically, if you want to be really correct about it, we're going to round these. So it might be easier to take either the floor or the ceiling of these. Here I'll take the ceiling of these numbers. Now, if we know the position in the camera frame relative to the world, that says X world, well, we go from the camera frame and we need to rotate it into the world frame and then add some offset. Where is the camera in the world frame? But if we know the world coordinates and we want our camera frame, we're going to have to invert that. And so all you do is subtract off this term. So we get X world minus OCW. And then we'll take that whole quantity and we'll multiply it by the inverse of this rotation matrix. So that's our world in C. And I'm going to go ahead and I'm going to multiply that out. This is our world in C times X world minus our world in C times OC in world. And so these define where is that camera frame. So these are the extrinsic camera parameters where we define that R is equal to R world in the camera frame, and this transformation is negative R world in the camera frame and O camera in the world frame. And so we can take this same equation that we had here and we can rewrite it using these extrinsic camera parameters. And so it's just R times XC plus T. And those are some unknowns that we don't know. There is 3 DOF rotation, 3 DOF translation. Very commonly, we use something called a pan tilt gimbal for the camera. If we do that, then we have a rotation around the world z-axis, so RZ of theta, and then we have a tilt about the camera x-axis. So that's the current frame, so post multiplies x of alpha. This theta is the angle between our x-axes, and this alpha is the angle between our z-axes. So let's combine all these things that we have so far. We've got that U is equal to lambda of XC over ZC. And then we have that negative U over SX is equal to R minus OR. Well, we can combine those two. And we can solve for our R value. And so lambda XC over ZC over SX plus OR is equal to R. So R is equal to negative lambda over SX times XC over ZC plus OR. And similarly, our C is going to be negative lambda over SY times YC over ZC plus OC. Let's look at what our unknowns are. I don't know what my lambda is, or my SX. I don't know what my OR is, SY, or my OC. So those are my unknowns. Lambda, SX, SY, OR, OC. Now we can simplify this a little bit because the only way that lambda enters in here is when it's divided by SX. And so we can just call those terms something new. We'll say that FX is equal to lambda over SX, and FY is equal to lambda over SY. And so now my unknowns are just going to be FX, FY, and then OC, OR. So the solution method for this is to acquire a big old data set. And the data set is going to have some row and pixel locations, and then their corresponding X, Y, and Z values in the world frame. We've got RI, CI. Those are my image pixel coordinates, and those correspond to XI, YI, ZI, which are my world coordinates in the world frame. Now just to remember, this unknown that we have here, this R and the T, there's 3 DOFs here, but there's 9 values that correspond to just 3 degrees of freedom. And then our translation is 3 DOFs as well. Just remind ourselves that x in the camera frame is equal to this r times x in the world frame plus t, where these are vectors. So we can split those out into our individual equations. So that, remember, this is xc, yc, zc is equal to r times x world, y world, z world plus tx, ty, tz. So we can write that out using our rotation matrix, and we have that r11 times x world plus r12 times my y world plus r13 times z world plus my offset tx. That gives me my xc. And similarly, r21 in x world plus r22 y world plus r23 z world plus ty. And finally, we have r31 x world plus r32 y world plus r33 z world plus tz. So we have these three equations. So let's take our equation that we had for r. Remember, we had that r is equal to negative lambda over sx, xc over zc plus or. Let's just take that term there. And let's move it over on the other side and subtract that off. And we can do a similar thing, saying that our c minus oc is equal to lambda sy, yc over zc. Well, we've got those terms now. This xc is given by this beautiful equation, and my zc is given by this equation. So I can just write those out here perfectly. It's just negative lambda over sx. So let's write that in here. We've got our r11 x world plus r12 y world plus r13 z world plus tx divided by r31 x world plus r32 y world plus r33 z world. I said x, I meant z up there, plus tz. On the other side, we've got exactly the same thing, only we're dividing our y-coordinate. So we can write our y-coordinate in. Y-coordinate is going to go there on the top. So I've got r21 x world plus r22 y world plus r23 z world plus ty. And so all this would be linear if I could take and have a new definition for where these principal points are. And so it's easy to do that by just defining a new variable. We're going to say that r prime is equal to r minus or, and that c prime is equal to c minus oc. And the reason we can do that is we know our principal point from the vanishing point. And so that allows us then to rewrite this equation down here, especially if we do our simplification, that this term here is our focal parameter. So then we can say that r prime is equal to minus fx r11 x world plus r12 y world plus r13 z world plus tx. And similarly over here, we've got c prime is equal to negative fy divided by our y-coordinate. I guess I should put in these w's. Work of a moment divided by r31 x world plus r32 y world plus r33 z world plus tz. Whew! So now we can solve for our zc. Remember, this bottom here is the same on each one of them, and set those two equations equal. R prime is equal to negative fx times x world over z world, and we've got that c prime is equal to negative fy y world over z world. So let's solve for these z worlds. Z world is equal to negative fx x world divided by r prime. Z world is equal to negative fy y world over c prime. We can set these two things equal. We get negative fx x world over r prime is equal to negative Fy y world over C prime. Then we can cross multiply here. And we get that C prime Fx x world is equal to R prime Fy y world. And then I can just write those out here. I've got C prime times f of x times my x world value is equal to R11 x world plus R12 y world plus R13 z world plus tx. Now we're going to divide both sides by Fy and define a new value as the ratio of alpha is going to be Fx divided by Fy. And we can multiply this all the way out. My R prime times this term and each term in term. And then we're going to subtract everything on this other side. That's going to be minus C prime alpha times R11 x world minus C prime alpha times R12 y world minus C prime alpha times R13 z world minus C prime alpha times tx. And that quantity is all going to equal 0. And so now we've made this equation where we've got a bunch of unknowns and a bunch of knowns. Let me highlight the things that we know. So we know our row coordinates, our row values, and we know our column values. We also know what our real-world coordinates are. Oops, that should have been lowercase. This term over here. And so the things that we don't know this term, 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 this term. And so what we can do is we can write this in the form of everything that we don't know. We're going to make some x. It's a bunch of parameters. And the things that we do know are going to be this large matrix A of our data. It's our data that we have transformed slightly, but it's still all things that we know. And what we'd like is for this equation to equal to 0. So it's just a game of putting together everything that you know and the things that you don't know. And so I'm going to put the things that I don't know in my list here at the right. Just starting from left to right, I've got my R21, I've got my R22, I've got my R23, I've got my TY, and then I've got the things that are multiplied by alphas. So I've got my alpha R11, my alpha R12, and my alpha R13, and then I've got my alpha TX. So those are all the things that I don't know. And then we build all the things that we know. And so we're going to do it for the first point that we have in our image. It's a row times its world coordinates. It's row value times y value. It's row value times its z world, and then it's a row. And then the next terms that we have in here are minus c1 prime times x1 world minus c1 prime times y world minus c1 prime times z world minus c1 prime. Let's do my next row in green just so I'm not confused. So you can easily build this row. All you have to know, what are my R values and my column values from my first point that I click on. Then I have to know what are my X values, what are my Y values, what are my Z values. And then I can build this first row of my matrix. And so then I just need to build my next row, which is going to be my second coordinate I click on, R2 prime, R2 prime, R2 prime, R2 prime, and then minus C2 prime, minus C2 prime, minus C2 prime, minus C2 prime. And then we put in our 3D coordinates of that. So it's X2 world, X2 world. This is Y2 world, Y2 world. I forget to put these things in here. And this is my Z2 in the world frame. And this is my Z2 in the world frame. And then I just continue that on for as many points as I have. All those in. And you want to have a big matrix because that way any errors you have can be averaged out. But the last thing in here is going to be my nth coordinate, the nth point I click on. So that is going to be Rn prime, Rn prime, Rn prime, Rn prime, minus Cn prime, minus Cn prime, minus Cn prime, minus Cn prime. And then we're going to put our xn in the world, our xn in the world, and our yn in the world, and our yn in the world, and finally our zn in the world, and our zn in the world. And then we've got this huge matrix that we built up for our endpoints. And then we ask our computer to solve that. And so you just say, here's my huge matrix A times my parameters equal to 0. And that's an easy system of linear equations for your computer to solve, and it'll get you your best approximation for what x is. It won't actually give you x. It's going to give you something x bar. This x bar isn't x, but it is close. It's going to be just a scalar multiple of the true solution. And what I mean by that is you're going to say that x bar is just equal to k times that true solution we want, which is going to be R21, R22, R23, ty, alpha R11, alpha R12, alpha R13, tx, quantity transposed. So here's our solution that we have. We have this x bar, which is equal to this quantity here, which is this constant times all the parameters we really care about. How do we get those parameters we really care about? Well, we can take advantage of the facts of things that we know. We know that this R is a rotation matrix. That means a lot of interesting things. For one of those things that we're going to say is that we know that rows are unit length. And so then we can look at these 3 units here. They would be unit length, but what we're actually getting is them multiplied by k. That's what this thing is over here. So then we can solve for it. The square root of these x bar locations, well, that is equal to k squared times r21 squared plus r22 squared plus r23 quantity squared. You can easily factor that out because this quantity here is unit length. That's 1. So that is equal to the square root of k. So we get the absolute value of k. So we don't know the sign, but we get the absolute value of k. We can similarly solve for what alpha is. We know that this alpha term here, so you've got alpha times this. This is 1, 2, 3, 4. This is 5, 6, 7 quantities here. So then we can solve for that. This is equal to alpha squared k squared times our quantity of r11 squared plus r12 squared plus r13 squared. And since this thing here is unit length, this is equal to just the square root of alpha squared k squared, which is just equal to alpha times k. And we do that by defining that this alpha is greater than 0. So now we need to solve for what is the sign of k. And so what do we know about our image frames so we can figure out what this k value is? Well, if a point is visible, then we know that ZC is greater than 0. So the scaling factor f of x is going to be greater than 0. Therefore, since we know that r prime is equal to negative fx of xc over zc, then we know that r prime of 1 over xc is equal to negative fx of 1 over zc. If we know that positive, we know that this term is positive, that means that this whole thing here has to be less than 0. And so all we do is we choose a k such that the sign of this, of our row value, times the sign of this quantity of our xc, which is equal to r11 x world plus r12 y world plus r13 z world plus tx. We just want to make sure that that is less than 0. So then we can solve for whether it should be positive or negative. From this, we have now solved for what our k value is and our alpha value is. We have solved for this row, and we've got our ty and our tx. That's pretty good. Now to solve for that third row, we don't have to do anything. Remember, it must be orthogonal, which means that all we have to do is take our first two rows and take the cross product. So that is r11, r12, r13, that transposed with the second row, which is r21, r22, r23 transpose. We still want to know what is this tz, and we also need to know what is our fx. It's still unknown. And so what we do then is we just redo our matrix equations. And we've got these two unknowns that we actually care about. So we're only going to, instead of grabbing and setting our r prime equal to c prime, we're just going to grab our r prime value. And then we'll multiply that out. It's a little bit tedious, but stay with me. So I know that ri prime times this quantity r31xi world plus r32 yi world plus r33 zi world plus tz, that quantity is equal to negative f of x times r11 xi world plus r12 yi world plus r13 zi world plus tx. And then we can put everything on the same side, so we have an equation equal to 0. So let's go ahead and do that. We'll do a little bit of multiplication out here too. I've got my ri prime times my r31 xi world plus r32 yi world plus r33 zi world. And then I'll put my first simplification here plus ri tz, and then we'll add the other side plus f of x times my r11 xi world plus r12 yi world plus r13 zi world plus tx. And so now the quantities that I really care about, the ones that I don't know, is this tz and this fx. Those are two unknowns, and then we've got another quantity over here, but this needs to be multiplied by the value 1. And then each one of them is multiplied by a parameter. And so we can set up something in the form of b y equals to 0, where b is all the terms that we know. I'll go ahead and highlight those for us. So we know this term, we know our ri, and we know all of this term. And then we take the remaining things, which are r1, our tz, and our fx, and we put those as our y column. And so again, we can build a monstrous data structure, then we can solve it out. And when we solve it, we're not going to get the direct answer. Remember, we're going to get a y bar, which is equal to a k, but we'll call it k2 times 1 tz fx. So this is just a scalar multiple of the true solution. That's not too hard to do. Let's go ahead and write that out. So y bar 1 is equal to k2, and y bar 2 is equal to k2 tz, and y bar 3 is equal to k2 times fx. So it's trivial then to solve for what our k2 value is. And then that means that tz is just going to equal to y2 bar divided by y bar 1. And that means that my fx is going to equal y3 bar divided by y bar 1. And so now we've got all the parameters. You have a wonderful day.